Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on causal inference. It's the second in a four-part series that addresses the matter. It's part of the course Analytic Methods for Lawyers, but like many of the videos in this course, it can really be used by a variety of people studying statistics, machine learning, and now causal inference. We left the prior video on a real cliffhanger, trying to figure out which of the various doctors trying to study some evidence on treatment of kidney disease was getting the right answer in terms of figuring out whether treatment A or treatment B was better. Today's video is going to resolve that question, as well as give you sort of a general recipe for figuring out when you can hijack traditional statistical methods such as regression or machine learning and use them to determine the strength of a causal relationship between two variables. We're going to be looking at things like weak paths, chains, forks, colliders, at the end, we're going to spend a little bit of time on the concept of d-separation and show how it can be used to examine whether a proposed causal graph could possibly be correct. You know, sometimes I think causal inference is a very difficult topic, and then other times I realize that an awful lot of the difficulty is due to vocabulary and the fact that there are essentially two schools of thought that don't talk to each other all that much, and this can lead to a lot of confusion. The two schools also themselves, of course, go by different names. And one of the schools is sometimes called do calculus, structural causal models. And if you see the name Judea Pearl, who's a computer science professor at UCLA, or you hear things like do calculus, you hear words like adjustment set, d-separation, you are most likely in the do calculus world. The other school of thought is called potential outcomes. It's associated with Neyman and Rubin. And if you start seeing things like average treatment effect, ignorability, propensity score, or notation like that, you're likely in the world of potential outcomes. This video is really going to be focused on the do calculus world. And then finally, we will spend a little bit of time in a later video on potential outcomes. And then we'll look at this sort of third thing, which is the world of econometrics, and we'll look at things like difference in differences methodology. This has the potential to be a very long video. There's a fair amount of material to cover, but in the interests of making the video something that you could actually watch, I'm going to go over some of the material rather lightly and trust that you'll take a look at the notebook that's associated with the video to fill yourself in. But we do need to understand what a graph is, and a graph is basically a collection of nodes and edges. Nodes go by different names. Sometimes they're called nodes, sometimes they're called vertices, same thing. And also graphs go by different names. Sometimes they're called graphs, sometimes they're called networks. For my purposes, same thing, and I think for most people's purposes, same thing. So what we have here is a picture of a possible causal network involving kidney disease, and the idea is that the size of the stone could potentially affect the treatment one receives, that the outcome from treatment is affected causally by both the size of the stone treatment and by the degree of support one might receive from one's family or an economic system, and that the outcome and the treatment in this model determine what ward you're in. The arrows denote the presence of a possible causal relationship. It doesn't really mean that there's a strong one or one at all. It just means it's possible. And so, in some sense, when you're talking about a causal graph, what you're really talking about is the complement of this. These are all the things that we are saying do not cause each other. Like treatment does not cause the size of the stone. The outcome of the treatment doesn't cause you to get treatment. When you see a causal graph, Just realize we're talking about potential causal relations. And if you see no arrow between two nodes, then you should know, for example, that support doesn't cause a change in the size of the kidney stone, and the size of the kidney stone doesn't, in this model, cause a change in support. Also, we're only going to be dealing with directed acyclic graphs. What is a directed acyclic graph? Well, it's a directed graph, and a directed graph means that all the edges have a direction. There are no bidirectional or non-directional arrows or edges. All the edges have a direction. Acyclic means that once you leave a node, there's no way of getting back. There are no cycles if you follow the arrow direction. So if I leave treatment and go to outcome, I can go to ward, but I can't get back to treatment because the arrow is going the other way. Or similarly, if I leave size and I go to outcome, I can't get back to treatment. So there are no cycles in this graph, and that's what makes it a directed acyclic graph. There is research in the field where you relax some of these assumptions, but it makes matters yet more difficult, and we're going to focus here only on DAGs. Okay, some quick vocabulary. Nodes have descendants. Those are all the places you can reach, starting at a node. The immediate descendants are called children, so treatment and outcome are children of size. Ward is a descendant of size, but it's not a child of size. Similarly, nodes have ancestors. And so here, the ancestors of outcome are treatment, size, and support. They're also, as it happens, the parents of outcome, because they're the immediate ancestors. If you had something that determined the size of the stone, such as exposure to, I don't know, lead, that would be an ancestor, but unless it had an arrow going into outcome, it wouldn't be a parent of outcome. Okay, that was graph theory in 2 minutes. Let's do set theory in 2 minutes. The idea of a set is an unordered collection of items. So the set ABC is the same as CAB because we don't care about the order. ABCC is not a set because the element C appears twice. It's sometimes called a multiset, but it's not a set. You should also know there's something called the empty set, which has no elements. It's sometimes written as an empty list. It's sometimes written as this O with a diagonal line through it. There are operations you can do on sets. The ones I want to focus on here are intersection and union. So the intersection of two sets are the elements that they have in common. So ABC intersection with, that's what that symbol means. B, C, D, E, let's see. They don't have in common because it's not in this one. B, yes. C, yes. D, no. E, no. So the intersection of ABC with B, C, D, E is B and C. Okay? And if you've worked with Venn diagrams, you've worked with set intersection. If two sets have no elements in common, they are said to be disjoint. And I'm showing you here, there's various code that lets you implement these set concepts in Wolfram language. Subset. A subset of a set is a set, and all of the elements of the subset are contained in the bigger set. So AB is a subset of ABC, but ABE is not a subset of ABC because E is not a member of ABC. And we can find all the subsets of a set with the subsets command, so the subsets of ABC are listed here. Set complement is sort of like subtraction. It's what elements are left after you take out the elements here. So if after I take out B and E, I'm left with A, C, D. Okay, so that was set theory in 2 minutes. Now let's get to the main action, which is finding valid adjustment sets. I'm going to speak about adjustment sets for the moment in terms of linear or logistic regression. You don't need those statistical techniques to have adjustment sets, but I think it's easier to understand that way. And the idea is that we want to basically hijack traditional methods, things you've seen already in this course, like linear regression, like logistic regression, and to take the findings from those models, and where it says, for example, that the probability of a good outcome has a log odds coefficient of 1.7 for treatment A, and to be able to say that means actually under these circumstances, when you've controlled for these variables, the adjustment set, that log odds coefficient is causal, that it actually causes a corresponding increase in the probability of a good outcome. So you may have learned at various points in your life that correlation is not causation and regression doesn't prove causation, and that is true. However, if you do the regression correctly and you make some important assumptions, then you can take observational data, things like the kidney study that we looked at in the prior lecture, and tease out the strength of causal relations. You don't need an expensive or sometimes unethical randomized controlled trial. Instead, you can just look at data after the fact. So the main goal of this part of the video is to figure out how to compute an adjustment set. And you can think of that as what other variables to include in your regression so that you can then use those variables plus the variable that you're trying to determine the causative nature of as basis functions in the regression. Okay, so there are a number of ways of doing this. I am going to give you what I think is the modern approach. It's from Professor Emilia Perkovich. And the nice thing about it is once you practice, you can, for modestly sized graphs, you can actually do it with your eyes. And once, if you have a computer and computer language, then you can do it algorithmically. All right. I'm going to read you the definition of the Perkovich criteria, and it's not going to be understandable, but due diligence says I should do it, and then we're going to walk our way through and see how it works. I actually think this is one of the things that's much easier to see with examples than with mathematical formalisms. All right, but here we go. A possibly empty set of vertices Z is a valid adjustment set for determining the causal relation between nodes X and Y in a graph script capital G if. Let me just stop there. Let's see what we're trying to see. What we're trying to determine is whether some set of vertices, or nodes really, I should be consistent, is a valid adjustment set in determining the causal relation between nodes X and Y in a graph G. So let's look at our picture here. What we're trying to determine, supposing we're trying to determine the effect of treatment on outcome. That seems to be what they were all fighting about in the hospital, whether treatment A was better or treatment B was better. And so what we're interested in is treatment in that Perkovich model is X, outcome is Y. What we're trying to figure out is what other nodes, size, support, reward, what combination of those, or maybe none of them, are a valid adjustment set such that when you do a regression in which treatment is included, the coefficient in front of treatment gives you the strength of the causal relationship. When it says that the log odds of an outcome are increased by 1.4 as a result of having treatment A, that really means that if you shift someone from treatment B to treatment A, it will cause an increase of 1.4 in the log odds of a successful treatment. If treatment's not causal, or there's more things going on and you don't have a valid adjustment set, then that coefficient will not give you the right answer. And when you shift from treatment B to treatment A, you may be rudely surprised. Okay, so let's go down, continue. A possibly empty set of nodes Z is a valid adjustment set for determining the causal relation between nodes X and Y in a graph script capital G if 1. All non-causal paths between X and Y are blocked by Z. All right, there's a second criteria. We'll get to that. All right, so let's look at this. We better figure out what a path is. We better figure out what it means for a path to be non-causal. And then we better figure out what it means to be blocked by Z. All right, so figuring out what a path is isn't too hard. Let me go back up to the picture and we'll just look at it. There's a path if, from treatment to outcome, if you can get there by following an edge, even if you have to, but you're allowed to disregard the direction of the edge. Only this in this area. But so, for example, treatment to size to outcome is a weak path because I can do it. I just have to ignore the fact that the arrow goes the other way. Treatment toward to outcome is a path because I can get there. I just have to ignore the fact that the ward to outcome arrow goes the wrong way. And treatment to outcome is a path. It's directly connected. I don't have to disregard any directions. So those are the only three paths from treatment to outcome. Okay? Just to make sure you understand, what about going from size to ward? What are the paths? Well, we can go size to outcome to ward, size to treatment to ward, size to treatment to outcome to ward. Those are all the paths. In this example, I didn't have to reverse any directions. I could just go straight on the arrows. Okay, so that's what a path is. And very thoughtfully, there is, let's just see, a resource function, weak path graphs that will take a graph, take your starting vertex, take your ending vertex, and it will find all the weak paths between them, and it will represent those as graphs. So if I run this, you should see the output already, but there they are, okay? And by the way, there's this thing, path graph string, which gives you a simpler, sort of a more concise representation of the paths. You'll often see diagrams like this in texts. All right, here's a database that has the paths. All right, so now we know what all the paths are, and let's go back to our definition. Our definition is we have to see if all non-causal paths between x and y are blocked by z. So now we know what the paths are. Now we just have to figure out if they're causal or not. And actually, this is pretty easy. If you can get there without reversing the direction at all and going against an arrow, then it's a causal path. So treatment to outcome is causal. Outcome toward treatment is not causal because I'm traversing this edge in a reverse way. I'm really not supposed to do this, but I let you do it at first, but now when it comes to figuring out if it's causal or not, this is not a causal path. Similarly, treatment to size to outcome is not causal because I have to go the wrong way on this edge, okay? So we can separate our paths into causal paths and non-causal paths. There's something else that I want you to notice, and that's that the path can be conceived of as a sequence of triples in which you have, at least if it has more than two nodes in it. And there are only a couple of kind of triples that can exist. There's a chain where you have the arrow going into the middle vertex and the arrow going out of the middle vertex, and they're in the same direction. You can have a collider. Look at 2, 3, 4. In 2, 3, 4, 3, it's being hit from both sides. The arrows are colliding with each other. So that's a collider. And 3, 4, 5 is right. 3, 4, 5 is a triple. But here it's called a fork. The arrows are both coming out of the middle vertex. And those are the only possibilities. There are no other possibilities for a directed graph. It's either a chain, a collider, it's either a chain, a collider, or a fork. And once you recognize those, you kind of know what to do with them. Okay. Okay, I'm now going to skip some material and talk to you about how to block a non-causal path. Though we only want to block non-causal paths. If you block a causal path, you will completely mess up your regression because you'll have prevented whatever causal relationship exists from showing up. So please only block non-causal paths. And we've got 3 rules. First, a path is blocked if any of its triples are blocked. You don't have to block all of them. You just have to block one of them, and often it's a good idea to only block one of them. Second, how do you block a triple? You block a triple if it's a fork or a chain, and it's a member of that set Z. So if you have a set Z and it hits a fork or a chain, those vertices are blocked, and any path that contains them is blocked. All right, so that's the second rule. The third rule is the hard one, and it's a triple is also blocked automatically if it's a collider. So don't block colliders. And neither it nor any of its descendants are members of Z. So if you block a collider, you will actually open the non-causal path, and if you block a descendant of a collider, you will also unblock an otherwise blocked path. And those are the 3 rules you need to know. I know they're a little hard in the abstract, but let's take a look at it, okay? Let's take a look. Here are our 3 paths from treatment to outcome. This one's causal, and there's nothing to block. There's nothing in between that we can block, so leave it alone. Second, here's another path, treatment toward to outcome, but ward is a collider. This path is already blocked by virtue of ward being a collider. So whatever you do, don't do what Dr. Eager did, which was to include ward in his regression. Bad idea, as Dr. Pearl pointed out. Let's look at this path. Treatment to size to outcome. Size is a fork. This is a non-causal path with a fork. This path is open unless I make size a member of the adjustment set. So, in this example, the only thing we need to include in the adjustment set is size. So our regression is going to, if we want to have causal treatment, we're going to have our 2 features be treatment, because that's what we're measuring, and size, which is the member of the valid adjustment set. You might be asking, well, you haven't said anything about support. Could you include support in the regression? And the answer is yes, you could, just as Dr. Liberal wanted to, remember after his zillion-dollar study. But remember how it didn't actually change anything about the regression coefficient? So that's fine. You can include support, and you might get some additional predictive abilities as a result, but you don't have to if what you're concerned about is a causal relationship. Okay, we're feeling good. We learned how to block all non-causal paths, but there's this terrifying second part. We have to make sure that there's nothing in Z, our adjustment set, that's also in the forbidden set. And the forbidden set isn't defined in the abstract. It's the forbidden set of X and Y, the cause and the effect in your graph G. All right, so let's figure out what the forbidden set is. And again, it's actually not that hard. Where do we have to go down to? Here we go. All right, so here's the deal. Go along the path from X to Y. Skip X itself. And make sure that Z doesn't have any of the nodes along that path or their descendants. And then also, you don't want the adjustment set to include X itself. So it wouldn't make any sense if you're regressing outcome on treatment to include treatment as an additional variable. It's already in there. You don't need it. And so let's look at our picture. Let's look at our causal graph and, or I'm sorry, our causal path, which is treatment to outcome. So we skip treatment, we go to outcome, and we certainly don't want to include outcome as a variable in our regression. That would be ridiculous because then we would be predicting outcome on outcome. But we also don't want to include any descendants of outcome in our regression, like, for example, Ward. So Ward is a member of the forbidden set. And therefore, even if it wasn't a collider, it would still be improper to include it. Okay? So we block all non-causal paths by blocking at least one of the nodes in any of those paths. And then you make sure that in the process of doing that, you don't also include in Z any of the nodes along the causal path from X to Y or any of the descendants of the nodes along that path. Okay, so this is actually a very easy example because the path from treatment to outcome is direct. Let's actually now look at another causal graph and see if we can figure out how to put this all. Okay, we're feeling good. We learned how to block all non-causal paths, but there's this terrifying second part. We have to make sure that there's nothing in Z, our adjustment set, that's also in the forbidden set. And the forbidden set isn't just defined in the abstract. It's the forbidden set of X and Y, the cause and the effect in your graph G. All right, so let's figure out what the forbidden set is. And again, it's actually not that hard. Where do we have to go down to? Here we go. All right, so here's the deal. Go along the path from X to Y, skip X itself, and make sure that Z doesn't have any of the nodes along that path or their descendants. And then also, you don't want the adjustment set to include X itself. So it wouldn't make any sense if you're regressing outcome on treatment to include treatment as an additional variable. It's already in there. You don't need it. And so let's look at our picture. Let's look at our causal graph and, our causal path, which is treatment to outcome. So we skip treatment, we go to outcome, and we certainly don't want to include outcome as a variable in our regression. That would be ridiculous because then we'd be predicting outcome on outcome. But we also don't want to include any descendants of outcome in our regression, like, for example, Ward. So Ward is a member of the forbidden set. And therefore, even if it wasn't a collider, it would still be improper to include it. Okay? So we block all non-causal paths by blocking at least one of the nodes in any of those paths. And then you make sure that in the process of doing that, you don't also include in Z any of the nodes along the causal path from X to Y or any of the descendants of the nodes along that path. Okay, so this is actually a very easy example because the path from treatment to outcome is direct. Let's actually now look at another causal graph and see if we can figure out how to put this all together. All right, here's our causal graph, and let's see what the causal effect of variable 3 is on variable 6. Okay, let's find all the path graphs. Here's another causal graph. Let's get the weak path graphs from 3 to 6. That just controls the size of the results. All right, and you can see there are a number of them. Here's our direct causal path. Here's a causal path. This one isn't causal because it's got a fork in it. Anyway, let's write a little function that says what we want to do is for some start and for some potential adjustment set z, we want to see if there are any possibly causal paths that aren't blocked. So let's evaluate that. And let's see. Let's look at our graph. And here we go. So if we don't adjust for anything, these are potentially problems, okay? We have a fork here, and to me it looks like we need to block one. We've got a one acts as a fork here, probably want to make one part of the adjustment set. Here's another one, one's a collider here, so actually, I'm sorry, one is a fork, strike that. So again, we probably want to block it, and one is once again a fork. So what if though I actually put 1 and 2 in the adjustment set? Would that be a problem? And the answer is apparently not. The only thing we have to make sure of is that neither 1 nor 2 is in the forbidden set. And we could probably do this by eye. If we go down our causal paths from 3 to 4 to 5 to 6, it doesn't look as if 2 is a descendant of any causal path. So I think we're fine, but we can certainly ask the machine to figure it out. And so there we go. The intermediate positions are 4, 5, and we also want to include 6. And we'll take a look at what are the descendants of 3, 4, 5, and 6. It's 3, 4, 5, and 6, and so 1 and 2 is disjoint from the forbidden set. And so 1 and 2 is a valid adjustment set. You could notice, by the way, that 1 and 5 would also be a seemingly valid adjustment set, but 5 is a member of the forbidden set because it's on a direct causal path there. So we don't want to use 1 and 5. And by the way, there's an automated function that I've written, causal graph forbidden set. And so now what we can do is there's a function I've written called valid adjustment sets, which saves you all this trouble now that you know what you're doing. It will take a graph, a starting point, treatment, and what you're trying to predict outcome. It will find the valid adjustment sets. You'll notice there could be more than one valid adjustment set. It's also possible that in certain circumstances there won't be any, like if you're trying to figure out the valid adjustment set of predicting what treatment you receive based on what outcome you had, there are no adjustment sets that work. So how do you know which adjustment set to pick? And there's no correct answer to that. Some people would say to pick sort of the most minimal adjustment set, just use size. But there's a recent article that I rather like, which suggests a different method. And the idea is to look at the parents of all the causal nodes, which by which we mean, for example, here, the causal nodes are simply outcome. Treatment is not itself a causal node. You look at the parents of them, support and size. So those are possibilities, but then you subtract out, you complement out, I should say, anything that's in the forbidden set, and the forbidden set is outcome and reward, and therefore, since neither outcome nor reward are in the parents, we don't have to worry about it. And so they would say that support and size are the proper adjustment set. The theory of this author is to try to basically maximize the R squared in a way that still gives you causal effect for the variable that you cared about. So there's a little function here that implements that. Okay, so if we go back to the prior video where there was that big debate among the hospital experts about how to figure out whether treatment A or treatment B was better, and they looked at a whole bunch of regressions, we now know what the right answer is and who was wrong. Dr. Eager was wrong in suggesting that we adjust for Ward. Ward is a collider, and therefore controlling for it is going to mess up the outcome. The correct decision is either to use size, and of course treatment, in trying to predict outcome, or size support and treatment in trying to predict outcome. And just to be clear about how you do control for variables, in a regression you just include them as basis, as one of the variables you're regressing on, and include that variable in the basis functions. The other thing you can do is to stratify. That is, for example, supposing, as is the case here, that size is discrete. You could look at the mean outcome of people for combinations of size and treatment and see if there was a difference in the mean probability of a good outcome. Okay, and so here I'm just showing you how you would do the logistic regression, and if you do it properly, for example, this, I'm just using size as an adjustment set, that's proper. What it turns out is that this value in front of treatment A is a good estimate of the causal effect of shifting from treatment B to treatment A on the log odds of a good outcome. You might ask, well, this is a causal model, so does that mean that negative 1.26 is a good estimate of the causal effect of having a large kidney stone? That is, if you could force people's kidney stones to grow, would negative 1.26 give you the log odds change of a good outcome? And the answer is no. You only get a causal effect for the thing that you tested the adjustment set on. If you want to do size and see what the causal effect of size is, you're going to have to go back and figure out what a good adjustment set is for size, and that might be a good exercise for people to practice on. By the way, if you do say, well, this is we've got a valid adjustment set, and so all of these figures are causal, that is sometimes called the table 2 fallacy. So don't commit the table 2 fallacy. The last thing I'm going to do in this segment is to do a logistic regression on another valid adjustment set, size and support. And what we can see here is that it doesn't really change the coefficient. As between different valid adjustment sets, the causal effect should remain essentially the same. Yeah, the R squared is going to be a little higher because you've added some additional information which may be marginally relevant to the success of the treatment, but the causal effect here, it's 0.35662, and up here it was 0.357229, essentially no difference. We started out this lecture with a causal graph, but where did that causal graph come from, and what if the causal graph is wrong? This is kind of the issue of causal discovery and deseparation, and I would say this is a field that is somewhat in its infancy. The first answer is basically the causal graph came out of my head, or out of doctors' heads, thinking about the logic of what causes what. But of course we could be wrong in that causal graph. Maybe, for example, it is, let's go back to the graph, not this graph, here we go. Maybe support actually also causes the treatment, and so therefore our graph is incomplete. All right, so How do you know if your graph is bad? You might not be able to prove your graph is good, but it turns out that there are ways of figuring out if your graph really can't possibly be right. And this is the idea of D-separation or conditional independence. And here's the thought. Instead of blocking all non-causal paths, block all the paths between x and y. If after doing that, and you regress y on x, or you do some sort of machine learning where you try to figure out what y is based on x, you should not be able to make any progress because you've broken every possible link between x and y. That is, x and y should be independent, conditioned on z. That's what this notation means, is independent of conditioned on z. So, for example, can we de-separate size from ward? Okay, and so let's look at our graph. All right, so to separate size from ward, we have to block all paths. And I would say if I control for outcome and treatment, there's just no way to get from size to ward. So if I now regress ward on size, outcome, and treatment, the coefficient in front of size should be, close to 0, or I should say its p-value should be higher than 0.05. If you're seeing that it looks like size does have an effect on ward after controlling for outcome and treatment, there's something wrong with your graph because there's some way or other that size is connecting to ward. Maybe there's an ancestor of size that connects to ward and there's a backdoor path to it. So this is how you can test for D-separation, and although it can't tell you that your causal graph is correct, it can tell you that your causal graph is messed up. If we do this here, let's actually do it. We're going to regress ward, which I'm going to turn into a number, based on size, outcome, and treatment. And we will do our logit model fit here. And what we're going to see is that the p-value in front of size, which is what we care about, that's what we're trying to see about, is 0.15. And so you can't really say that it's non-zero. And so essentially we can't disprove the null hypothesis that the causal graph is correct. What we might like to do is to find all the conditional independencies in the graph, all the things that should be true if our causal graph structure is correct. Okay? I could not figure out how to get Wolfram language to do that. R has a package called Daggity that does this for you, and here's what it came up with. It says that size should be independent of support, size should be independent of ward, conditioned on outcome and support. That's what we sort of just figured out by hand. Support should be independent of treatment, and treatment should be independent of ward, given conditioned on outcome and support. And so we can actually test each of these four propositions. And if we start seeing low p-values for the thing, basically the thing on the left-hand side, we may have a problem. And you can look at this and know if I do size on support, our p-value is a healthy 0.45. If I do size, outcome, and treatment on ward, the p-value is what I found before. What about support on treatment? That's supposed to be conditionally independent, and our p-value is 0.7. Finally, let's look at this last one where we're trying to see whether support is independent of ward given outcome and treatment. Here's the logistic regression we run. We look at the coefficient in front of support. We look at the p-value. Again, it's over 0.05. And so there's nothing in that data that we developed in lecture 1 for size, outcome, treatment, ward, support that disproves the causal graph that we have been working with. The sort of analysis I just did is sometimes used to try and figure out what the most likely causal graph is given the data. In my experience, and I know I'm going to be hurting some feelings here, I've yet to see it be particularly successful in any practical setting. Perhaps in the future we'll be able to do better by figuring out the most likely causal structures based on the data. For right now, I think probably the best we can do is to say that the data doesn't falsify a causal structure that a human has deduced based on logical reasoning. I'm going to leave some material on potential outcomes for you to read, and I'm going to say that we're done. What we did is we learned how to take a causal graph and figure out basically what variables we need to use in a regression or what variables we need to control for in order to read causal effects out of standard statistical procedures such as regression. We also learned at the end about d-separation and how it can be used to attempt to falsify a proposed causal graph. I know this is difficult material. There is a lot of vocabulary, a lot of confusing definitions. I think if you practice trying to find valid adjustment sets, either using some of the code I have or in smaller graphs, just doing it by your eye, you actually get pretty good at it and it's kind of fun. So in the next video, we're going to take our little look at potential outcomes, and then we'll come back and look at some other aspects of causal inference. Thanks very much.